Thank you for passing the test back up. I'll grab those. I know some of us want to see more of this, but I need these for my next class, so if you want to come back. I'm going to pass back some your packet, which is everything you need for this last part of the unit. And we may not get to all this, but I'm going to try my darndest. I'll make the crossword. I want to go over some quick. I just have to prioritize. So I think a lot of this will resonate with you because you've already done your web class. Did you ever get one of these? Almost let me know if we're out. So whenever we talk about going to completion, we usually just write the reactants yielding the products, and that's it, single arrow. So if we have a reversible reaction, we're going to write a double-headed arrow, and that's what you'll see in a minute. What are some evidences of chemical reactions that you know show something goes to completion? Evidences of chemical reaction that shows something has gone to completion. Shout them out when you know them. Huh? How do you know something combusts, though? So, gas evolution, flame, fire, heat, those are more specific terms. Okay, so heat evolution, gas evolution, maybe cold, so change in temperature. Those are some things that show chemical reaction occurs. Okay, a lack of energy. Yes, ma'am? I'll get you two more. Yeah, just a second. So these are some things that we know. What else? We got like kind of the combustion around here. Precipitation, color change. Anything else? That's a pretty good list. But, you know, I want you to remember some of the stuff from Unit 1 because we will talk about them more often. Some things that I specifically have told you before is gas evolution. So we've seen that. Formation of a pure liquid. And this is back from our acid-base equilibrium or acid-base reactions. What was a neutralization reaction specifically? Or just an acid and base. It doesn't necessarily have to be strong. So what's your favorite acid?
Sulfur.
Hydrochloric. Okay. Favorite base?
Water.
No. Water is not a. It's an acid and a base. It's not going to be a good base for us here. Potassium. Hydroxide. Good Lord. Whew, okay. So combine those for me.
HOH.
And?
KCl.
Okay. So here's my proof here. A neutralization reaction makes water, which is a pure liquid, and we label it by putting an L next to it. Pure liquids are going to be something very important to recognize here. And also formation of a pure solid, that would be like a double replacement reaction with a precipitate formation. So these are examples of things that go 100% to products, therefore we write them with a single arrow towards the front. Sometimes forming a precipitate actually, you know, we do know it does, we do know that it precipitates out. But sometimes it doesn't exactly stay precipitated, and I think we're going to talk about that either today or tomorrow. Yes, ma'am?
Could I please have Samara Archibald for dismissal, please?
Thank you.
Thank you.
Watch this video. Okay, so that's some of the information that we kind of already knew. This is the new stuff. Tell me, some of this is familiar from your web quest. Reversible reaction. What else is familiar? Dynamic equilibrium. Double-headed arrows. Anything else? Okay. The definition of dynamic equilibrium is that there is no net change in concentration of products and reactants. Do you remember the brackets mean concentration? Brackets mean molarity. So that's some stuff that's Not new to you, but new for us to talk about today. So there are going to be reactants and products left at equilibrium. And equilibrium is just a state of a reaction that we talk about, and it can be graphed, and now we can actually measure the concentration changes over time. We can do a lot of stuff like we did last week. So on the web test you guys did, you saw some graphs. Do you remember what those graphs look like? So one was going up and one was going down, and then maybe they crossed, maybe they didn't. But eventually, we do remember they flatten out. That is the point that we're really specifically focusing on today, and that's the flattening out, which is the no change, no net change in either product concentration or reactant concentration. So I'll actually draw these over here. So if you graph this out as concentration versus time, and I'll do reactants in red here. Generally, do we start with reactants or do we start with products in a reaction? Generally, we start with reactants. And like we said earlier, reactants will start to go down, and eventually they'll stop changing and they're going to level out. Products will be in green here. And so usually we start off with 0 products, and they'll go up. And then when the reactants stop reacting, and that means they're going to start making products, so they'll level out. So the point at which it reached equilibrium was right at the place where the flattened out slope occurred. So this is at equilibrium here. And so in this case, can you tell who is favored? It's the formation of product favor or the formation of reactant favor in this graph. Take a stab at it. Give me 50-50, and then you got a 50-50 chance, and I'll explain. Why products? They're favored because there's more of them, right? You're making more of them. So the products are favored because more at equilibrium. You guys remember what that means for the K value, which you investigate a little bit on your equilibrium part of your web quest. I'll give you a hint. K is either greater than 1 or K is less than 1. Take a stab at it, people. Greater than 1. Okay, so K is greater than 1 when the products are favored. And that's what the graph looks like. And if you see a graph like that, you immediately should be able to tell that the products are favored simply because there's more of them versus the reactants. And that means the K value is greater than 1. So knowing that, let's reverse all that information. You tell me what the graph looks like for reactants favored. Concentration versus time. I hope you're sketching some of these because they'll be helpful, specifically in your multiple choice part of your test. So we'll use the same colors. So what happens, how do I start here? Do I start in the same places or do I start in different places? Same, because I'm starting at the same, meaning the reactants are still going to be starting me off. And I'm going to go down with the using up of concentration of the reactants, and then I'll flatten them out. Okay, and then the products are going to be forming. Now, here's the point where I need you to help me. Do I cross the line or do I stay below the line? So I can get really close. I can even converge, but I'm going to stay below in this case because I told you specifically I wanted products down low and I want reactants on top. So I can definitely tell in this graph that the reactants are favored. Why? Just because at equilibrium there are more of them, and equilibrium hit at the same spot here. Right here, I'm at equilibrium, at the flat spot now. So K is what here? K is less than 1. Okay, so these are facts you should be able to pull from a graph fairly quickly. Now, whenever I say that one side is favored over the other, that just means that I'm going to be more likely going in the forward direction if I'm forming products, or in the reverse direction if I'm favoring the formation of reactants. It can go back and forth. So do you guys remember the last part of your iodine clock reaction lab where it took forever to turn? Yeah? and some of them started to turn kind of purpley, and then you swirled it, and what happened? It went back clear again, right? That is a reversible reaction, and that's because the concentrations are so close to what they are at equilibrium. When you swirled it, you shifted it back towards the reactant side, so it turned back clear versus that dark purple color. And so the whole reaction, all of the ones that you guys did, everything before that was very, very, very concentrated, so we forced the product's formation. But when you got down to the nitty-gritty, we got to the point where we started to favor reactant conditions, and we'll get into that, like how you shift that in a minute. So there are two ways to write equilibrium arrows. You can write them just reversible like this, or you can actually show the favorability. So what is this one showing? Favoring products or reactants? Definitely favor products. And so if you see the favoring products, you assume K is what? Greater than 1, right? And if you see this one, what do you know? Right, you know that you're favoring reactants and that K is less than 1. So there's only one time when K is equal to 1. K is equal to 1 when both reactions are equally favored. And usually, it depends, but usually products will equal reactant concentrations. There's other ways to make K equal to 1, but generally that's mathematically how it works out. And I'll show you how the math works here in a second. I really like equilibrium. It's easy math. It's like addition and subtraction. Maybe we get a square root in there every now and then. Okay. So, we just did that. Yay. Oh, the one part I didn't tell you is what the K value means. So you already wrote this down, but this is what the K value means. You wrote this down probably in your web class someplace, but it's the extent of the reaction in the forward direction. And so if K is greater than, and K has a name, it's called the equilibrium constant. I'm assuming a lot though, so if you're like, we still think you're speaking Spanish to us, let me know that, because I know you have a little bit of background right now. So K is called the equilibrium constant. Yes. You're at the wait. Just if it's emergency, let me know. K is called the equilibrium constant. It does help us determine if products are favored or if they're not. So if the products are favored, the forward reaction, the extent of the forward reaction is very, very, very large. In the web quest, did it go through how to calculate a little bit of how to set up the expression for K? Something with products versus reactants? Okay, I'm going to show you right now, okay? How do you calculate K? I'll give you the basics of it first. K is equal to the concentration of products over the concentration of reactants. And I want you to tell me mathematically that this makes sense. It totally does. If you're math-minded, you're like, it's so easy. So if I have a lot of products and very few reactants, that K is going to be a lot over a little. Is that K value going to be greater than 1 or less than 1? Greater than 1. So K greater than 1 means I have a lot of products. Well, you already know a lot of products means it's going to be top on the graph, so the products are favored. So mathematically, K bigger than 1 means that I have a lot of these. Not the denominator. So then K less than 1, need some space to write here. K less than 1 means I have a little on top and a lot on bottom. Well, who's on the bottom? The reactants. And if reactants are large, what's a small number divided by a large number? A number less than 1, right? A decimal. K is less than 1. So mathematically, it agrees with each other. It's actually pretty nice because you have quantitative and qualitative agreement. All right, so here's how we actually write out the K expression from an actual DCE. And I will practice some more of these in just a second. This comes from a law called the law of mass action. You don't necessarily need to know that verbiage, but I need you to know how to write out the K expression. So I like to call this the K expression because it's actually, there are no numbers in it, it's just the BCE's information. So using this reversible reaction I have here, I know you're like, oh yeah, A plus B yields C plus D. We write concentration of products raised to the exponent. So K is equal to concentration of, tell me one of the products. One of the products? C, and that's capital C, raised to the little c power. So the little c is an exponent here. Okay, so then tell me the other product. So capital D raised to the little d power. So the coefficients in the BCE are important. That's why I want to make sure you balance it first. So those are the product concentrations divided by, when you're ready, concentration of A raised to the little a power, and the concentration of B raised to the little b power. So it can get more involved depending on how many reactants and products you have. The only time you ever exclude a reactant or a product is if they are pure solids and liquids. So omit these. Don't include. And that's because whenever the reactants and products are liquids or solids, can you get a concentration for a solid? It's got to be moles of solute over liters of solution, and a solid is not a solution. So you cannot get the molarity for it. The molarity is constant. Constant or incalculable. And so pure liquids are the same way. You can't have like moles of water over solution of water, right? It's the same thing, and that's why we don't include them. So when I say the word molecularity, I'm referring to the coefficients here, and that's why we transpose them over here as exponents. Can I scroll down a little bit? Everybody with me? Okay. In the end, sometimes I'll just ask you, what does the K mean? And the K means simply the ratio of the products versus the ratio of the concentration of the products versus the reactants. So we'll just say we'll say it's a ratio of molar concentrations. And that's just a kind of a easy quick phrase to represent what K means. And from the K value, or the equilibrium constant value, we can find the actual favorability of products versus reactants. We're going to write some K's here in just a second. Oh, actually, I passed these out. You see on your particular, the front side of your sheet, which says Unit 8, Student Packet, Worksheet 1, write the equilibrium expression for the following. There's A and B. Go ahead and write the equilibrium expression, the K expression. So on your paper, you're doing A and B, 1 and 2. A and B. So first off, I want you to double check, are there solids or liquids in the first one? Nope, so I'm going to include everything. So what am I putting on top for this one? So the concentration of H plus to the first power, right? Okay, I'm not going to write the AQ. We don't need to. We're assuming it's not solid or liquid. Times what? The fluoride ion. Okay. Those are in the numerator. And then do what? So divided by HF, right? Hydrofluoric acid. All right, now this is actually an interesting one. This is regarding the dissociation of an acid. You know it's an acid because there's an H plus in the front, right? Or an H in the front. That acid dissociates to 2 different ions, but not 100% because you see the double-headed arrow. So what kind of acid is that? Is that a strong acid or a weak acid? Weak acid, right? And a lot of times we'll actually denote the K with a little subscript to say what it's talking about. Well, this is talking about an acid. So you write Ka. It's just sometimes more informative to write Ka versus just K. All right, so let's do this one over here. You guys tell me what I'm writing. K is equal to, so the first step, always your first step is like say, do I have pure liquids or pure solids? Yes. Okay, so do I write this? No. I actually just put a scratch to it so I kind of up front know I'm not writing it. So if I have no products, what do I put in the numerator? A 1. It's just a placeholder. Okay, so the 1 is there over concentration of hydrogen gas squared. Good, because that 2 there is going to be now an exponent times O2 to the first power, right? Okay, so this one actually deals with gases. You can write a couple different things here. You can write KEQ to represent the equilibrium constant. You can write KC to represent concentration of blah 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 gases in this case. Okay, these all really, they're just interchangeable. They mean the same thing. KP is an interesting one, and I'll show you how to write the KP expression. KP, what do you think the P stands for? Pressure. And the pressure part is going to look a little different. So I'll write that down here. KP for the same B right here, okay? All we do is change concentration brackets to P for partial pressure. So if we were given pressure in this problem, we would do 1 over partial pressure of hydrogen gas. What still goes up here? 2 squared, okay? So that 2 is squared, or the hydrogen gas is squared, and the partial pressure of oxygen to the first. So these two things are interchangeable. It depends on what kind of information is given, pressure or concentration. And we'll start calculating with them here soon. All right, thumbs up if that makes sense so far. Okay, coolio. Let's go back. This one right here, these take a couple minutes on these, okay? You can write this you might not be able to fit it on here. You might be able to fit it on the bottom or on a separate sheet. Go for it. Work with the person next to you. Talk about it if needed. Oh, and actually, we just did the lies. Never mind. That's good. Keep going. I'll just say we did the first one, but we did not. That's a 2 and that's a 2. Yeah. Yeah. That's a solid. I really tried to write neat here. Solid, gas, gas, gas. And then carbon most of the time is like graphite and solid. So if something is a gas, you need to.
Oh, no.
Okay, guys, tell me what you got for 3 here. 3. K is equal to concentration. What's the name of that? Carbonic acid, so H2CO3. Remember, it's products of reactants, not reactants over products, over what? Concentration of CO2. Why not water? Right, it's a pure liquid, so do not include it. How about number 4? K is equal to concentration of magnesium ion. Okay, so times bromide ion squared over. And actually, on this one, don't put anything over it. Don't even put over 1. I'm just going to write it as is, because I learned this year, we do this in AP Chem too. Last year, they did not give points on the AP Chem exam if you put over 1, because you assumed something was there, but it's a pure solid, so you don't include anything. I don't know why, but I'm not doing it at this point. How about the last one, number 6? I mean, you may not have gotten this far, but go with it with me now. K is equal to, what's the name of that? Hydronium ion times, what's that? Acetate, C2H3O2, 1 minus, over acetic acid, concentration of acetic acid. And then liquid water is irrelevant, we don't write it. Okay, this one is actually an acid dissociation, acid equilibrating to its 2 ions, so I'm going to call this one Ka. Yeah. No, I just didn't do number 5. I just did 2 or 3, 4, and 6 right now. I will, are you asking what to do? My bad. K is equal to 1. Sorry, but only because it's 1 over 1. I got your question now. I just didn't do number 5. Yeah, liquid, solid, and solid, it does not have anything in its calculations. All right, so this is Ka. This one right here is a solid dissociating to 2 different ions. That one's actually called the solubility product. Product in math means what? Multiply, right? And the solubility is, how does it dissolve, right? It dissolves into ions. And so when you multiply the ion concentrations, that's called the KSP, or equilibrium solubility product constant. So that's called KSP. So sometimes I'll show you the names, and they're not all that relevant. I mean, they're relevant, but you don't necessarily have to write them down, but you'll start seeing them more often. Okay, do we feel okay with writing products over reactants? It's not difficult. Let me make sure there's nothing I missed that I really want to do. No, there's not. So let's start to calculate with them. This one's on your sheet. It's on the left-hand or right-hand side. So whenever something is at equilibrium, we know there's some products left and there's some reactants. Those some products and some reactants sometimes are given to us in the problem. it's very, very helpful when it says the equilibrium concentration. So when it's like screaming at you, the equilibrium concentrations are given, that's great, because those values, that's what K is talking about. It's talking about the concentration of the products at equilibrium and the reactants at equilibrium. So these values are what we plug into K to actually calculate K now. So I'm going to do these first two with you, and then we'll try some by ourselves. So here we are. This is the same, nope, not the same problem. I don't have any space here, so I'm going to write down here. So here's our reaction. The very first thing I'll say is read it. What do you see is given to us? So the molarity for phosphorus, what's PCl5? Pentachloride. We got the molarity for phosphorus trichloride and chlorine gas. Chlorine gas, okay. So the question is, what is the value of the equilibrium constant? What is that asking for? K. All right, so we need to always remember, like, what is equilibrium constant? It's asking for K. And then it says, are the reactants favored or the products favored? So that before I would do anything, is my first step is always to set up K expression. So K is equal to, I'm ready when you are, write this one down for yourself. Looking at the BCE, what's the expression? Phosphorus trichloride. Chlorine gas. Okay.
The concentration of phosphorus
Pentachloride. I got you. You're good. Yeah. Okay, so we have our K expression. So step one, set up K expression. What do you think step two is? Plug it in, plug it in. Let's do this. These are really quite easy once if the equilibrium values are given to you, and that's why I want you to make sure you're reading equilibrium concentrations. They are given to you. Plug them directly into the K. EQ is what I'll call this one because it's equilibrium. So what am I plugging up top? Thank you for getting your calculators out. What's my one that goes in here? 0.229 molar. Next, chlorine. 0.229. Ooh, I want you to notice this. You'll notice they're the same values, right? Why? Say what? Well, how about when things react, right? They make a certain number of products. They make them in the same ratio. Do you see that they're made in the same ratio? They're made in a 1-to-1 ratio, so if they're made at the same time, they're made in the exact same amounts as well. So that's why that's the same. Over what? 1.271. All right, you guys tell me what that is when you get it. I believe you. What'd you say? 0.0412. Arm stop in there. Anybody confirm? Verify. Okay. So this is the K value. One fun thing about equilibrium is that they are unitless. This is K with no units. Yay! No units. Okay. So if this is our K value, yes, ma'am. It means first of all, it's the equilibrium constant, and it means it's the ratio of products versus reactants at equilibrium. It means more than that, but that's the basic of it, okay? So looking at this ratio of products versus reactants, obviously you can tell it's less than 1, right? K is way less than 1. Products favored or reactants favored? Reactants are highly favored. And you can tell that because look at the numbers. 0.229, 0.229, 1.27, highly favored because there's more of them. So then what would the graph look like? Would they cross or would they stay like this? That, right? Okay. There we go. All right, so that's not bad. If the numbers are given to you at equilibrium, you plug them directly in. Let's look at the second one. This is y'all's second one. Please tell me I'm right here.
Yes.
Okay. So, in gaseous equilibrium, blah, 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 when it says that gaseous equilibrium, it's telling you that all of these are gases. Gas, gas, gas. Okay. The equilibrium concentrations of A, B, and C are blah, blah, blah. What is the value of K? You guys do this one. Use your same two-step process. You gotta make sure you're really watching your parentheses on these. Did everybody get this setup correct? The K expression? C squared over A squared times B. And then plugging, it says respectively, so make sure you're plugging them in correctly. What I would recommend is putting this in the numerator and then divided by a bracket or double parentheses or something. 5.5 times 10 to the negative 3 parentheses squared, because if you don't put the parentheses at the end of that, it's going to only square the times 10 or 10 to the negative third instead of the 5.5 as well. And then end it with a bracket. What do you guys get? Whenever you're there. What'd you get? 8, 7 times 10 to the negative 5? 9. Anybody else get that? It's hard to put these in. You gotta practice. I have no idea. I have to check. My calculations are in my book someplace. That could be right. I have to say that double check. 1.528 times 10 to the third. Anybody? I'm going with that one. All right. So we found the value of K to be about 1,500. Is K greater or less than 1? Greater. So who's favored? Definitely products. And you can tell because it's 10 to the negative second versus 10 to the negative third on these, which are lower. So the products are favored. Okay, so we've learned how to set up our K expressions, how to plug in equilibrium concentrations. Now let's look at something that maybe gives us an initial concentration before the reaction begins. And then we let it react and do its thing. And then where our job is to figure out the equilibrium concentrations that we would normally be plugging in here. That's not this one. That is number 3 on your sheet in front of you. Number 3, which is says given. I just need to scooch forward a little bit here. I'll come back to these. Here. Is this number 3? Yeah. Number 3. It says 2A plus 2B yields C plus 4D. Write the equilibrium expression, and then it says initial concentrations are given. So you guys write the equilibrium expression. Shout it out for me. I got a couple people getting sleepy on me, so I need your help here. K is equal to concentration of C. D to the 4th power over A squared and B. Oh, my bad. Sorry. I'm not. You guys can see this better. Yeah, D is definitely a solid. Let me just erase this. This is on your paper, yes ma'am. It's number 3 on the left-hand side. All right, so first of all, scratch D. Like, just put a mark through D so you remember it's a solid. Wasn't watching myself. Thank you for catching me. 2, I heard A squared, and then what else? So concentration of B squared. Okay, so we have our expression. Now we have to set up something called an ICE box. An ICE stands for initial, change, and equilibrium. So I'm going to actually rewrite my BC because I can't work with that little bitty thing. So 2A plus 2B equilibrates to C plus 4D. And here's how you draw an ICE box. ICE, and it's actually just an addition and subtraction system. And all you do is write down the initials that are given and the I, and then if you know information for E for equilibrium, you plug stuff in there as well. So the initial concentration of A was what? 4.0, right, so 4.0 molar. The initial concentration for B was also 4.0 molar. The question is, what would the constant be? So what is it asking for?
C.
The constant B? It's asking for the equilibrium constant. So what's it asking for? Yeah, the question is K. Because they had to set up K. We're going to get values and we're going to plug it back in K and actually solve for K or calculate K. All right, so what would the constant be if at equilibrium 2 molar of A has reacted? So at equilibrium 2 of A has been reacted. So here's, let me remind you, I don't want that one anyway. This is initial, this is change, and this is equilibrium. Okay, so if 2 has reacted, that means in the change part, 2 molar of A has been subtracted, has been reacted. So this means to subtract 2 molar of A. So I'm going to subtract 2 molar of A right here. Subtract. Well, what do you notice about A and B? I know they start off initially the same, but what else do you notice? They both have a 2 coefficient. I heard kind of that. So they both react at the same rate. So if 2 of A got used up, how much of B do you think got used up? 2 as well, because they react in a 2-to-2 ratio. Okay, so before this reaction begins, how much product do you think we have? 0. Like, I have 0 products at the initial because it didn't tell me I had any. And plus, I start off with reactants. I let them react to make products. I don't have any of these originally or initially. All right, here's the fun part. So if I have the knowledge of how much reactants were reacted, I can figure out how much products are made. So if this reacts in a 2-to-1 ratio, and 2 of these get subtracted, first of all, we know that we're adding to the product side, because we're making products, we're forming them, but how much C is made? How much? Why 1? Right, I make 1 of these as I use up 2 of these. So if I use up 2 molar of this, I'm only going to add 1 molar of this. And I'll show you a cheap and easy way to do this. Whenever we subtract things, we call them X's. There's 2 X's that were subtracted here because it was 2 times something, and we don't. Since sometimes we don't know it, we call it X. So I'll put it right above this, minus 2X. And this one, minus 2X. How many X's are added here? 1X, because there's only a coefficient of 1 here. How many X's are added here? 4 X's, because there's 4 coefficient here. So you can probably tell me, if I subtract 2X here, and I already know what it's worth a total of 2, then what is X worth? 1. And that's why I added 1 here. But you could figure that out from your division as well. Okay, so if this reacts in a 2-to-4 ratio, how much do you think is added here? 4, because I subtracted 2 here, so I'm going to add double that on this side, so that's 4. Okay, at equilibrium, what do I have? 4 minus 2 is what? 2 molar. 4 minus 2, 2 molar. What do I have here? So 1 molar and then 4 molar. Which of these is irrelevant? I made us do it, but we actually don't need it because it's not important here. Okay, so then the information I have at equilibrium concentrations go in the equilibrium expression. So it took us a little longer, but we got our equilibrium numbers. We can plug them in here now. So K is equal to what goes on top? What goes on top? 1, because it's C's concentration goes in here. Now, I'm not even going to put the molarity because K is uniless. Over 2 for, we're talking about A, right? And then what happens to A's concentration? Squared. And then B? 2 as well. It's also squared. Sorry, mine's a blob there. Okay, so what's 2 squared times 2 squared? 16. What's 1 over 16? 1 or 0.00125 or something like that. What is it? It's below 1. Whatever it is, it's below 1. So K value is 0.006 or no 0.0625. There we go. Very less than 1, so reactants are highly big. All right, so can you guys start 4? Start 4, which is right below 3. I would set it up eerily the same. Look up here. Has everybody gotten this far? What else have you added here already? Okay, so you knew that 0 and 0 if the products were initially present. What else? You know you're adding it? How do you know you're adding it? Because it was produced, so I hear you adding this. I'm actually going to put it down there first because it says at equilibrium 2 molar of C is produced, so that's at the E mark, and so that's why I originally put it there. But then you guys are super smart, and you're like, well, how did it get there? I added that amount, so I added 2 molar here. Okay, so here's the next part. You guys kind of tell me what you know, so where can you proceed? Okay, so if C is adding 2, since it's a 1-to-1 with A, I'm subtracting 2 here. Are you guys cool with that? It's like a puzzle, right? So you know you're subtracting 2 here. So you know that at equilibrium you have 3 minus 2, which is 1 molar here. What else do you know? Yeah. Well, there's a 3 there, but it's in a 1-to-3 ratio. So here's where like I said, I'm an X person. Tell me how many X's, just based off the coefficients, how many X's are subtracted from A? 1X. How many X's are subtracted from B? 2X added to C. 1X added to D. 3X. Can you tell me what X is worth? How do you know? Well, because I subtracted 1X here, and that's subtracting 2. I added 1X here, and that's 2. So X is equal to 2. So if you know what X is equal, you can do the algebra across the board versus guessing, well, I think it's going to add 3 here because there's a 3. That coefficient can throw you off. It's useful, but it's not the end-all be-all. So if I'm subtracting 2x's here and x is worth 2, how much am I subtracting here? 4. I'm subtracting 4. So it's 8 minus 4. 4. And I'm making my x's small so that they don't distract you right now.
Teachers, please pardon the interruption. At this time, please send all rising seniors to the auditorium for their registration assembly. Once again, please
I'm gonna finish
send
this
all
problem.
rising seniors to the auditorium for their registration assembly at this time. Students, be sure to bring your registration materials with you. You will not return
I'm
to
getting
third
ready to
period.
tell you.
Thank you.
Right now, my juniors, we're doing 5 and 6, which are right below where we've been working, and then on the other page, 11 through 13. That's it. Work on that. Mythbusters, lab report, due Friday. So which ones are we doing? 5, 6, 11 through 13. I'll update the website. Bye. All right, guys, let's finish this right now, okay? Juniors, go that way so you can. Don't distract us. Everybody else who's left, tell me what I'm adding over here. Adding over here. Adding 6 here because it's 3 times x. And then what is it total here? 6 molar, right? Okay. So plug these into our equilibrium expression. K is equal to 2 to the first, okay? Times 6 to the third, because D was cubed over 1, and that's nothing, and then 4 squared. Can you try to do this without your calculator?
Okay, so
Let's try.
36 times 6.
So 36 times 6 is
156. No,
192. What is it? So hold on. 30 times 6 is 180.
16. It's 16. You're wrong. 36 times 6.
30, no, hold on. I'm talking about 36 times 6. So 30 times 6 is 180, right?
Plus 36. 186.
Plus 36?
Yeah.
Oh, 6 and yeah, so.
Okay, 36
So
times
206. No, 216. 216 times 2 is 432. What's 432 divided by 16?
26.
What is it, Hannah?
27. So close.
Thanks. Okay, so K is 27. So products are favored. All right, so ice boxes, we are okay with figuring out how the changes work and what the equilibriums are?
No.
Okay, you guys right now work on, you only got a couple minutes left, but work on 5, 6, 11, 12, and 13.
Are you open for it?
No, I haven't been there. Excuse me? Because there's like a million other places to be, specifically like your teacher's classrooms for tutoring. Not yet, because I forgot to pick theirs up. I'll pick that up tomorrow. Yeah.
Wait, are you open for B?
I have quiet lunch for B. And people left trash at my back lab station last week. So, well, I don't know who, but you guys have groupie responsibilities. So